In this last section of chapter 3, we're going to be taking a look at the idea of these related rates. And what is a related rate? Well, we know that the derivative is indeed a slope, and we know a slope is just a rate, okay, something over time. And just as an example, let's say for some reason we have a really basic geometric object, okay? So let's just say we have a snowball or something like that. It's in the shape of a sphere, and I know this isn't a good example of this. But let's say for some reason we put that snowball into some sort of heating, or we just bring it inside. Well, we know over time, so let's say after 3 seconds, it's going to start melting a little bit, and it might look a little bit smaller. And then after 6 seconds, it's going to get even smaller than that. All right, so, and eventually it's just going to keep decreasing, etc. All right, so that's the idea of what a related rate is. In other words, the volume is dependent on the time. Okay, so the volume of the sphere, we know the volume of our sphere is going to be 4/3 pi r cubed. All right, and so what we can say is that it's dependent upon the radius as well. So the volume is related to the radius, and the volume and the radius are contingent upon the time. Right? So the volume is dependent on time, the radius is dependent on time, and that's what a related rate is. It's how do these two variables, or even more variables, affected by a specific time? In other words, is it growing, is it shrinking, that sort of thing. All right, so that's what a related rate is. And essentially what we're going to do is we're just going to multiply by derivatives, all right, with respect to time. So there's a change of volume with respect to time, there's a change in the radius with respect to time. And they just become regular old variables for us. So we're going to take a look at some really basic examples, and we're going to just work our way up to more difficult ones as we usually do. So a really basic example of this, we have the sides of a square. They're increasing at a length of a rate of 4 meters per second. What is the area of the square changing when the sides are 17 meters, and at what rate is the area changing of the square when the sides are 27 meters long? All right, so everything's in meters, so that's good. We know that the area of a square is equal to any of the side squares. So that's the first thing we need, is we need some sort of formula to represent the elementary geometric relationship. Now, what we're going to do is to be able to find the rate of change, right? We're going to take the derivative of a, which is 1. But what we're going to do, very similar to implicit differentiation, is we're going to multiply that by the change in the area by the change in time, right? Because that's what it is. It's a related rate. So it's going to be 1 times dA dt. And then on the right-hand side, we know that the derivative of s squared would be 2s, but we're also going to multiply that by ds dt. Right? So anytime we take a derivative with respect to a related rate, we're just going to multiply by the differential divided by time. Now let's go back up to the top of the problem. Right away we know that this is going to be 4 meters per second, and the sides are changing. So this 4 meters is actually ds dt. We also know that s in part A is going to be 17. And all we're going to do is we're going to substitute those values back in, and that's going to help us to be able to solve for dA dt. So what we're going to say is that dA dt is going to be equal to 2 times s, which is 17 meters. And then also, we can say that the sides are increasing at a length of 4 meters per second, so that's going to be multiplied. So this is the s, and then ds dt is going to be the 4 meters per second. And now all we do is we just multiply that out. So dA dt is going to be equal to 2 times 17, which is 34. 34 times 4, that should work out to be 132, I believe. So let me just do it all to the side. 17 eighths, 6. Okay, so sorry about that. It's going to be 136. So this is going to be 136 meter times meter, meters square per second. All right, so One of the things we want to make sure of is that because it's a change in area, we do have a square value going on with this. Right. Now for part B, at what rate is the area changing when the sides are 27 meters long? All right, so we're going to use the exact same formula, dA dt, and that's going to be 2, not times 17, but times 27 meters. And we still have 4 meters per second is going to be the rate of change for the sides of the square. And so we just multiply those together. And I might have to do this off to the side again. So this is 27 times 8. Again, that's going to be 56, and so 216. So this is going to be equal to 216 meters square per second. And that's our dA dt. All right, so hopefully that makes a little bit of sense to you. A really elementary example of this. Right? Now, another elementary example. The area of a circle increases at a rate of 5 centimeters squared per second. So we want to know how fast is the radius change? Is the radius changing when the radius is 1 centimeter? And how fast is the circumference? Or what is the radius changing when the circumference? So we need our two formulas. All right. So first of all, we know that area of a circle is equal to pi r squared. Okay. And that helps us a little bit. And we also know the relationship of the circumference. Circumference is going to be equal to 2 pi r. All right, so let's see what we can do with this. All right, so when we go through and do this, first of all, for part A, and by the way, this is 5 centimeters square per second. That's the area of a circle is increasing. So that's going to be dA dt is going to be equal to 5 centimeters squared per second. Right? So part A should be really easy for us. So let's just go ahead and do that. So we're going to take the derivative. We have our A equals pi r squared. And we take our derivative. So the derivative of A is 1. But just like we did before, we're going to multiply by dA dt. And then the derivative of this pi r squared is going to be 2 pi r. And we're going to multiply that by dr dt. And then now we're going to substitute back in with what we know. Now we know that the radius is 1 centimeter. Right? So, and we know dA dt is 5 centimeters squared per second. So this is going to be 1 times 5 centimeters squared per second is equal to 2 pi times r. And r in this case is going to be 1. And then we have the dr dt. And this is going to be, by the way, this is going to be 2 times pi 1 centimeter. All right, so I forgot to put the unit in there. Now what we're going to do is we're just going to divide everything by 2 pi centimeters because we're looking for dr dt. We're looking for how fast the radius is changing. So we divide by 2 pi centimeters on both sides. And so we have a centimeter and a centimeter that's going to cancel out. And so the answer for us is going to be 5 over 2 pi centimeters per second is equal to dr dt. Now the second part, how fast is the radius changing when the circumference is 6 centimeters? All right, so that's a little bit trickier. All right, but here's how we're going to do this. First of all, the circumference is 6 centimeters. So let's plug that immediately into the formula because we don't know what the radius is. All right, but that's okay. We don't really need to know that too much. So this is going to be 6 is going to be equal to 2 pi r. And we're just going to divide everything by 2 pi. So 6 over 2 pi is equal to r. So that's the radius. So right now we know that the circumference is going to be 6 centimeters. Then the radius is going to be 6 over 2 pi for this problem. And it's helpful because the only formula we have for circumference is this 2 pi r. Now, it does lead to a problem because we don't know how fast the circumference is changing, all right? So that might be a little bit of an issue for us to be able to work through. So how fast is the radius changing? So let's go through. We have our circumference formula. So circumference is equal to 2 pi r. And at this point, we're just going to say dc dt, so that's the change in the circumference, is going to be equal to, so we take our derivative, and that's just going to be 2 pi dr dt. All right, so we really didn't even need to find the radius, at least for this problem. All right, now the circumference is 6 centimeters. All right, but that doesn't necessarily help us too much, just because, well, we don't know the change in the rate of the circumference. All right, so how do we finish this one out? Well, what we're going to have to do is we're going to have to pause the video because it's almost done with time allotment. And what I'll do is in the next video, I'll show you how to finish this one off.